Welcome everybody to this meeting of London Futurists. London Futurists is all about looking at some of the scenarios that are just around the corner, which might be radically different from what we're used to. Looking at some of the technologies that are here today, but which might be even more powerful and even more useful quite soon. We're trying to figure out which of the stories about the future are credible, which of them actually have a lot of scientific backing and which we should look at. Which of these stories about the future are attractive? Some of them at first sight might seem a bit strange, some of us might go, ooh, but then when we think about it more, we might say, actually, no, this could be a good future. And one of the most radical and interesting futures that we often hear about is the possibility that we could have a lot longer youthfulness. So instead of just having youth for a few decades, and then having a few decades of middle age, and then going downhill pretty rapidly, we could have regeneration, we could have rejuvenation. And one of the possible keys to rejuvenation, and there are several, is this fascinating field of stem cells. And I'm very pleased to say that we have, I think, one of the world's experts in stem cells, not just a theoretical expert, but also a practical expert in stem cells here today, Dr. Stephen Minger, who has a background in academia, as well as a very strong footing in the real world of commercial companies. In fact, he has been hired by one of the world's most successful companies, GE, which goes all the way back to Edison, and which has done remarkable things in many decades, and is now looking at health. So there is a significant division, health sciences, and Stephen Minger has been chosen to be the chief scientist of this, bringing his knowledge into that field as for the development of potential therapies in the short term and also looking further ahead. So let's give a warm round of applause to Stephen Minger.
So good afternoon, everyone, and thank you for coming out on a wonderful winter day in London. Apologies, I've just come off a month of long-haul flights. I've got a really bad cold, so I probably will have to stop numerous times and blow my nose. I'm sorry about that. I want to keep this as interactive as possible. I'm going to try to be as provocative as I possibly can be, something I'm known for. And also, my views don't necessarily in full reflect GE's opinions, okay? So I'll point out very clearly when I'm talking about things that we're doing at GE, and other times I'll talk about work that we did at King's, or what I want to try to do is bring you up as up to date as I possibly can as to where the field is actually at. I've been attending several gene and cell therapy conferences in the US and trying to push cell therapy, for example, in places like Saudi Arabia. So I want to try to get you up to speed with where the field's at, but also reinforce the idea that the controversies around reproductive technologies and stem cells continue. And I want to try to point out parallels between what's happening this week here in this country around three-parent embryos versus some of the things that happened with us a few years ago. So by way of background, just so you have an understanding of where I come from, in the mid-'80s when I was doing my undergraduate degree at the University of Minnesota, I got heavily involved in neurosurgical brain mapping. So this was the pioneering neuroepilepsy clinic in Minnesota, where we were actually going into human brain and mapping out high real estate areas, as we refer to it, with the hope of being able to remove seizure foci from patients who unfortunately had their seizures in their dominant hemisphere. I then spent 3 years as a technician in a bone marrow intensive care unit, solid organ transplant unit, so I got very interested in the idea of cell replacement, organ replacement. You'll see why that's appropriate in a moment. Then did my PhD at Einstein in New York, where in a very prominent Alzheimer's lab with a Brit named Peter Davies. We pioneered the development of some of the first animal models in Alzheimer's disease. But I realized in my lifetime we would probably never understand the mechanism of how Alzheimer's disease happens. And so I then moved to a lab that had pioneered in Lund the use of human fetal tissue in patients with Parkinson's disease, where you transplant back in replacement tissue from aborted embryos. There are patients in Sweden who were transplanted 30 years ago almost now, who have never gone back on anti-Parkinsonian medications. The grafts are very effective. The problem is it just takes a huge amount of fetal tissue to do this. So the idea was, when I went to La Jolla, could you take material from aborted embryos and somehow figure out how to expand it in the dish? Instead of using the equivalent of 12 fetuses to treat one patient, could you make one fetus into 12? So this whole idea of cellular expansion, even back then. And we were the first group in the world to be able to go into the brain and actually take cells and be able to expand them to very large numbers in the dish. Something that is now slowly but surely heading toward the clinic. I then moved to the UK in 1995, set up a stem cell lab. The rest is history, as they say. And I joined GE Healthcare about 5.5 years ago for a lot of reasons. One, they came shopping for me. Two, they made me the proverbial offer that you can't refuse. How would you like to have almost unlimited amounts of research money without ever having to write another grant? Those of us in academia, I think we can relate to this very easily. I spent the last 10 years in academia doing nothing but writing grants, trying to support the 15 people in my group. This used to be my boss, John Deneen. He has left recently, and we have a new CEO of healthcare. And then the other big aspect was the access to all this technology, in particular diagnostic imaging, the use of MR, CT, PET, SPEC, ultrasound, the ability to be able to image inside a living human body without having to open somebody up. So this was really, really crucial. But in actual fact, whoops. Wow, I'm missing a slide. That's not very good. Okay, that doesn't matter. In actual fact, the larger General Electric is made up of almost unlimited technological prowess. We make nuclear reactors, we make jet engines, we make light bulbs, we make Harry Potter movies because we own Universal Studios. The technology breadth within the company is just massive. And when you think about applying all of that to regenerative medicine, cell-based and gene-based therapies, you can see the appeal of leaving academia and heading for a commercial company. And I'll show you what we've done in the interval. So when I was brought on board, it was to run a spin-out company within GE Healthcare called Cell Technologies. And very simply, it was to pioneer the use of human cells, and in particular human stem cells, to really advance the field. Okay, so I'll tell you what stem cells are in a moment, so don't worry. And I'll show you how we've used this in a number of different ways. But really, it was designed to use cells as tools. Could we develop cell-based assays that could improve drug discovery, could improve the safety profile of medicines that we're taking through the clinic, using human cells as opposed to animal cells? And I think we've been very successful in doing that, and really the pioneer in that field. Cell-based therapies. Now this, I think, is really provocative because if you go back 10 years ago, when GE just began healthcare, somebody had the bright idea that GE should be a cell therapy company. Now when you think about it again, that seems pretty far-fetched. We make light bulbs, we make jet engines, we make nuclear reactors. Now you want to be a cell therapy company? When I first heard about this, I thought, this is crazy. Whose idea was it? But you'll see at the end, we really have become a world leader in developing technology that will allow us to be able to grow any cell that has therapeutic potential, whether harvested from you and expanded outside your body and put back, or from classes of cells that are derived in other ways. And I'm going to take you through this whole technology so you really understand it. And at any point, if I'm not making sense or you think I've said something you don't like, just yell out and we'll have a discussion, okay? David really likes these things to be really interactive, and I do as well. And then I'll show you how we've used really pioneering automated microscopy, the use of microscopes that basically run themselves, that can look at billions and billions and billions of cells a day in a very automated, fast fashion to again improve drug discovery and the ability to generate tools that may be useful in developing cell-based therapies. Right. So that was 5 years ago, 5.5 years ago, and then we've undergone several reincarnations since then. We bring new technologies in, we spin old technologies off. This is now called life sciences. It's about a quarter of healthcare. So it's about 10,000 people worldwide, and the research budget is about $300 million, okay? And I'm chief scientist for all of this. And it ranges from stuff that is just basic lab stuff that we use every day, molecular biology tools, fluorescent dyes we use to image cells, through regenerative medicine and cell-based therapies. I'll talk a lot about that. We have a big and long-standing relationship with big pharma, particularly in the manufacturing of kind of new generation drugs, which are called monoclonal antibodies and therapeutic proteins. So things like erythropoietin, which you give to people to boost their red blood cell production, or new biologics, which are kind of the new generation of drugs, which are not pills, they're actually antibodies, living protein that we inject into patients, particularly for cancer. A whole thing on diagnostics that I'm not going to talk about very much, but it's the ability to be able to take 10 guys that you think might have prostate cancer, take a single thin section from their tumor, and then interrogate that for maybe 50 or 100 different markers. And now instead of saying prostate, 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 and give them all the same drugs where only 2 of those patients will actually respond, you now say this guy has this type of prostate cancer based on this molecular signature, he gets that drug. Somebody else also has prostate cancer but has a different set of mutations, maybe a different set of chromosomal abnormalities, wouldn't have responded to this drug, I'm now going to give them this drug. This is a whole new way of diagnosing what we call precision medicine, and GE is pioneering that. And then, as I said, imaging, using MR, PET, SPEC, etc. So this portfolio is all of mine, and I can pull different bits of it in from various places, okay? So, stem cells. Stem cells are unique cells that are unlike most of the cells in your body. You have approximately 100 trillion cells in your body. But believe it or not, you have 10 times as much bacteria. So you're 90% bacteria. We think of ourselves as being quite unique, in the world, but we are literally 90% bacteria. And people have ignored this for years, but this is a brand new emerging field of something we call microbiomic diagnostics. That is, you are what lives inside your gut, and probably a good degree of disease susceptibility, obesity, inflammatory bowel disease, and even potentially cancer development is based on the composition of bacteria in your bowels. So, and we finally refer to this as shit diagnostics, but it is becoming something really, really big, okay? Nevertheless, out of the 100 trillion cells in your body, probably less than 1% of them are stem cells. And stem cells have 2 major defining characteristics. One is they are cells that can divide. Most of the cells in your body are made, they live for a certain period of time, and then they die. Okay? So if you think about your skin, think about your hair, think about the cells that line your intestine, probably cells in your brain to some extent, cells in your heart. Our bodies are undergoing this constant attrition of cells. It's been estimated that if you live to be about 80, there are about 9 of you standing next to one another of all the cells in your body that you've ever made in your lifetime. And the only reason you do that is because you have cells in your body that are capable of dividing, and when they divide, they recreate one cell that remains as a stem cell and one cell that becomes what we call a somatic cell or a differentiated cell, okay? And then when that differentiated cell dies, another stem cell will divide, replace the cell that's been lost, but replace itself. And that's why even if you live to be, say, 100 or 120, you still make blood cells every day, okay? Any idea how many red blood cells you make every second? 3 million. Every second of your life, okay? Think of the energy man, think of this stuff, Think about how much hair some of us make every day. Think of your skin, And the number of cells that you make on a daily basis is just astronomical, and it's because these cells are really, really active. We think when they get deranged, may again be one of the mechanisms of cancer development, whether they're stem cells gone bad or cells that because they mutate so much they go back to looking like stem cells, we don't really know. But these cells are very, very active, and they basically keep your body in homeostasis and replace all the cells that you need on a daily basis, okay? So they are capable of division, and they give rise to the cells within a tissue. So in your bone marrow, for example, where there are adult stem cells, you have blood stem cells that give rise to all the cells in your bloodstream. White blood cells, macrophages, monocytes, red blood cells, platelets, megakaryocytes, etc. And you do that continuously through life. You don't even think about it, right? It just happens, okay? You have another set of stem cells in your bone marrow that control that process called mesenchymal or mesenchymal stem cells. And if you take them out of the body, put them in a dish, and push them to differentiate, they can make bone and cartilage. So there are a number of companies and clinical groups in the world who are using these cells to make replacement bone and replacement cartilage. A lot of these are in late-stage clinical trial, and a couple have already been licensed by the FDA. So we can already make cartilage and bone from cells from your bone marrow. Fat, adipose tissue, contains fantastic numbers of stem cells, both hematopoietic blood stem cells and mesenchymal stem cells and others. And it's a constantly renewable source, right? And it's not as invasive as going into your bone marrow. Ever thought of fat as being a stem cell tissue? Okay. But there are companies now who do this routinely. They'll take your bone marrow, they'll take your adipose tissue, digest it, harvest the cells, inject them into your heart, inject them into your leg if you have critical limb ischemia, et cetera, et cetera, et cetera. Okay? So there are something on the order of about 4,000 clinical trials ongoing at the current time, registered in a database called clinicaltrials.gov. And then it's predominantly these kind of mesenchymal, or sometimes they're referred to as stromal cells, which are being used in a whole variety of different conditions, and some of which are proving to be clinically beneficial, and some of which they don't seem to work at all. Okay, then there's stem cells in the umbilicus, in the cord, and in the placenta. This has become a big money spinner for a number of companies who are basically encouraging parents to bank their child's cord blood at birth. Costs a couple £1,000, and then a few £100 a year to keep it on ice, as it's referred to. Whether or not you would ever use that for your own child remains to be seen, but lots of people do it, and it's something that I feel like parents get a lot of coercion to do this. And whether or not it's really ever going to be clinically useful, I don't know. Where it is clinically useful is as an alternative to bone marrow for patients who need a transplant because they have leukemia or lymphoma. The public banks that we have worldwide are notoriously very small, ridiculously underfunded by the government, and people don't even think about, if I'm not going to bank my child's cord blood myself, why not donate it to a public bank? Have you ever thought of that? Have you ever heard about it? No, because there's no advertising around this. We've worked really, really hard on this, and it's like, John the Baptist out in the woods. Nobody pays attention. Governments are not interested in this, and yet 90% of patients who are waiting bone marrow transplant will die because they don't get a suitable match. And here you have, a source of material that's free. It doesn't cost anything to obtain. It's at no risk to the child. It's not invasive. It's just when the baby's born, you cut the umbilicus, you drain the placenta, and you can bank that. And it's an alternative to bone marrow. It has the same population of bone marrow cells within it. So you got nice stem cells in the cord. You've got some adult tissues that have stem cells, like the bone marrow, the brain, fat, but not all tissues have stem cells. So if you get type 1 diabetes and your immune system wipes out your insulin-producing cells, those cells will never come back. And even if I know that you're going to get this disease early on, I can't take part of your pancreas out, put it in a dish, and expand it. There are no stem cells in the pancreas that anyone has ever been able to isolate and expand. And that's true of most adult tissues. Okay? Then there's one set of cells that causes all the controversy, and that is embryonic stem cells. Let me take you through that so you understand why this is controversial. So embryonic stem cells are called embryonic stem cells because they come from embryos. They come from a special class of embryos. They come from embryos that have been created by in vitro fertilization. So IVF, which won the Nobel Prize for Bob Edwards, who I was lucky enough to know a few years ago, is a pioneering technology where you will remove eggs usually from the woman who is fertile, put those into a dish, and then impregnate those with sperm, either from the partner or from a sperm donor, if need be. So fertility in a dish. You then grow the embryos in culture, usually until about day 3, and then you will pick the 2 best embryos based on morphology. So this embryo is really nice, it's got 8 single cells. It's not missing any, it doesn't look like some of the blastomeres, as they're referred to, are going away. And then you will implant those into the woman's uterus. Excuse me. And the remaining high-quality embryos generally then get frozen. Okay? Now, if the woman is particularly fertile, you may get 10, 15, 20 or more eggs from her in a single round of superovulation. Okay? You have to impregnate all of the eggs because you can't freeze unfertilized eggs very well. Technology is getting better, but certainly when we started this work at King's, 10, 15 years ago, you could not freeze eggs. So all the eggs get fertilized, so you may freeze 10, 12, 15 embryos. And at some point, couples stop their fertility treatment, either because it's been successful or not. And what you're left with are embryos sitting in the freezer. Now at King's, we did 500 cycles a year. Okay, so that's 500 rounds of superovulation and fertilization. And we would routinely get 5 or more embryos per couple, which means you may end up at the end of the year with 2,000 or more embryos still frozen away. And up until recently, you could freeze embryos for 5 years. So that means we had 10,000 embryos sitting in tanks of liquid nitrogen, which is a real pain to deal with logistically. And that's why occasionally the wrong embryo ends up in the wrong uterus. Because trying to keep track of all these embryos and making sure you don't put the wrong embryo back into somebody who it wasn't intended for is a real ongoing problem. The bottom line is, and there was a headline I saw this morning doing some research on this, something like 1.7 million embryos were destroyed in the UK, like 5 years ago. There are just so many embryos made that never get used. The vast majority of them are just discarded. Couples generally don't donate them to other couples, and the only other alternative is they can donate them for research. And up until 2001, the only research projects for which you could use human embryos were those that were for fertility treatment. So improving implantation, reducing miscarriage, etc. Because somebody had made embryonic stem cell lines in the US in 1998, we petitioned the British government to allow us to use discarded but donated embryos to make stem cell lines from. And the way this works is if a couple donates an embryo to us, we thaw it on day 3, we keep it in culture until day 6 when this event happens, which is called, this is a blastocyst, and this is called hatching. Prior to this time, the embryo itself is basically totipotent. It can make both placenta and it can make the baby. On day 6, what you see is a segregation of this set of cells called the inner cell mass and this larger set of cells here. This larger piece turns into the placenta. It cannot make an embryo or a fetus or a baby, but this can. This little population of about 30 to 50 cells is what turns into you and I. This is what we look like when we're 6 days old. Those of you who are good at measurement, this is about 100 microns across. You cannot see these with the naked eye, and it's very difficult to see them even with a really good culture microscope. Basically what you do is you isolate the inner cell mass away from the trophectoderm, and using special culture conditions, you put that one little population of cells into culture on top of what's called a feeder layer, and with an efficiency of about 10%, that will begin to grow. And then, so we were about number 8 in the world back in 2002 to do this under license from the Human Fertilization Embryology Authority. And when you get a single colony like this, you can't just let it go because it will either die or it begins to differentiate. So what you have to do is cut it up into little pieces and then move it. And again, that's when it's pretty tense because you don't get embryos that often, and even an efficiency of 10%, you lose quite a few. So we did this very carefully. You cut it up. When you're successful, you establish what's called an embryonic stem cell line. That is, it's a group of cells that come from a single embryo, and so all the cells are genetically identical. Okay? These cells can be propagated forever, ad infinitum. Okay? So you can grow unlimited numbers of these things. To give you some indication of that, this cell line was one of the first 3 that was created in 1997 in Wisconsin. Okay? Came from a single Israeli embryo that my colleague Joseph Ishkovitz brought over from Israel to Wisconsin, and they created this cell line. Okay? This cell line has been used by probably 1,000 or more research groups worldwide pretty continuously since 1997. The number of cells that have been generated from this would fill this building. I am completely convinced of that. We grow about 50 billion of these cells from this particular cell line every week in Cardiff. 50 billion. So from 30 cells from a single embryo, the number of cells that has been generated from the cell line is astronomical. Yeah.
What's the controversy?
Because it comes from an embryo that could have turned into a person.
Surely, since they decided to discard all those unused embryos, that's where the controversy belongs.
Yeah, that's a very rational argument.
It's true, the alternative is it will be destroyed.
Yeah, it would have been destroyed anyways, and that's always been our argument. You're preaching to preaching to the Pope here, you know. Okay, so what's unique about these cells? So I can grow lots of them. Who cares, right? What do you do with them?
Sorry, there's no mutation, no change at all.
Depends on how you grow them.
Okay.
You know, you have to treat them with kid gloves. I mean, these cells are difficult. It's like, when I tell people in my lab when they used to come to the lab and they say, oh, I've grown cells before. I said, no. It's the difference between growing tomatoes and growing orchids. Okay? These cells are really, really difficult to grow. If you look at them, if you come in a bad mood, they'll change. You know, if you don't play the right music, they change. Okay? That's why.
Presumably, in a sense, they want to differentiate, so the difficulty is stopping them.
Exactly. If you notice, this is very important. This is not, I mean, it's about having green fingers. The gentleman already up here has anticipated the next bit, which is, why are these useful? They're useful because they came from the inner cell mass, which can generate the entire fetus, baby, and you and I. These cells can make every cell type in the body, if you understand the process. Okay? And the big challenge, as he pointed out, is keeping them in this pluripotent state and not letting them just differentiate willy-nilly, because they will. If you just leave them alone, you don't take good care of them, come in one day and all of a sudden you've got neurons, you've got beating heart, you've got skin, you've got muscle, you've got bone, occasionally you have teeth, you know, ovaries. Okay, so controlling this process has proved very difficult. We were probably number 8 in the world, and we're only now getting to the point where we can fully control the differentiation of these cells into very specific cell types. The last 2 or 3 years, this field's moved really, really quickly. Okay. Now, GE is not involved in the generation of cell lines at all, and we only use cell lines that have been made previously and that have been approved either by the NIH in the US or the Medical Research Council here in the UK, excuse me, where those cell lines have been ethically validated as being appropriate to use. They've been donated under informed consent, no financial or medical inducement to the couples. They don't control how the cells get used, and the cells are freely distributed across the world. Okay? Now, there's a whole bunch of other ways to make the equivalent of those cells. Yeah.
Just quickly, going back to the previous slide where
Yep.
you said these can differentiate into anything.
Yeah.
Is there something about the inherent genes in the cell that means they'll only differentiate into the features of the donor person? So, for example, if they come from someone with blue eyes and red hair, that they will only grow into blue eyes and red hair?
That's a very interesting question. Clearly, they have the genome from the embryo. And say, for example, so we had an embryo once that came from a couple that had a child with cystic fibrosis, where both parents were carriers but didn't know it. They had a child by natural pregnancy and with a child with cystic fibrosis. They wanted to then have another child, but they didn't want to have the risk that their child would have CF. So they underwent IVF, and we screened the embryos on day 3 by removing one cell and looking at it genetically. And we could segregate embryos that had CF versus those that only had one copy of the gene and were therefore normal versus ones that were normal. That cell line has cystic fibrosis. Okay? Whether or not you can make it into a disease model in a dish that represents cystic fibrosis is another issue. But clearly, the cell line will have the genetics that the embryo would have had, for better or for worse. Nobody's made eyes and nobody's made hair, so I don't know the answer to that question. But clearly, any genetic presusceptibility to disease, any polymorphisms that lead to, unusual biochemical or behavioral phenotypes will be expressed in that cell line. And we'll come back to that in a moment because it's really pertinent to this slide that I'm going to put up next. So this was the state of the art back in 2002, 2004. You only are going to be able to make pluripotent cell lines from embryos. But what if there's somebody who's alive who has a very important genetic mutation. Okay, somebody who's got, I don't know, an incredibly rare form of cancer, an incredibly rare form of Alzheimer's disease. I'm not going to be able to make a cell line from an embryo because that embryo, in all likelihood, doesn't have that genotype, right? So what we wanted to do back in 2004 was to be able to make the equivalent of these cells, but now make them from pre-existing adult patients, people, okay? And that's a technique called therapeutic cloning or somatic cell nuclear transfer, okay? And it's actually quite simple. So here you see what I just showed you. You take an embryo, you isolate the inner cell mass, you make a pluripotent stem cell line that can differentiate into any cell type. Over here, what you do is you take an egg that's been donated for research, and you remove the nucleus of the egg. Okay? So now the egg doesn't have any identity. It's just a ball of proteins, right? Because the nucleus contains the DNA, which gives rise to our identity. The reason why we're each different is because we have different DNA. If I take the nucleus out, I now just have an egg. And if I take a cell, say from this gentleman, and I put into the egg, I've now transferred his genetic identity into the egg. It has the mitochondria from the egg, but we think the mitochondria, as you know, if you've been listening to the mitochondria debate on the 3-family embryo, it's a very, very small fraction of the genes in the entire organism, and probably doesn't mean that much in terms of having mixed genetics from the mitochondria to the nucleus. So I now have his genome in an egg, I give it a zap of electricity, it turns into a blastocyst, I now have a pluripotent stem cell line that's genetically identical to this gentleman. Okay? That makes sense? This is how we made Dolly the sheep, right? We took a cell from what was Dolly, the 6-year-old sheep, put into an egg, transferred the genetic identity into that egg, made a cloned Dolly blastocyst, put the blastocyst back into her mom, and Dolly came out the other end. We were all happy with that, right?
It's a stupid question, but I don't understand why you've done that. You've taken a nucleus from one egg and just put it into another egg which you've removed the nucleus from. What's the advantage?
So this cell is not from an egg. This cell is from you.
Okay.
Yes, a somatic cell means not.
So this is taking I can make a cell line from any of you guys that will have all the features of a cell line made from a blastocyst. That means I can grow it forever, and I can differentiate it into tissue that you might need for transplantation. Or if you have a unique disease, I can now use that to try to model that disease in a dish. Let's say you have Alzheimer's disease, a genetic form of Alzheimer's disease. I make neurons, and now and I know you're going to get Alzheimer's disease. There are genetic mutations that cause AD that are 100% dominant. You will get if you have this mutation, you will get the disease. So now I can try to model this in a dish. Okay, if I know what your genetic mutation is and I create neurons, will they give me an Alzheimer's phenotype like they would if they were in your brain? Okay, so that was why this was important. Yeah.
What's the success rate of that process?
It was incredibly low until my erstwhile colleague, Professor Woo-Suk Wong from Korea came along. Do you guys remember Professor Wong? The guy in Korea who made these cell lines and then they all turned out to be fake, right? But he also made Snuppy. He's the only guy in the world to successfully clone dogs. Okay? Woo-Suk had us convinced the efficiency was going to be about 1 in 10. It was not. He used over 2,200 eggs, all obtained fresh, never went through IVF, some from young women in his lab, some from egg donors, and he made 0 cell lines. And I'm really glad you asked me that, because this was our argument in 2005, was that, well, this had proved not to work. So, but we were going to the regulator to ask for the ability to be able to make cloned stem cell lines, but our ethical concern was we were going to have to ask women in toto to donate thousands and thousands of eggs for this procedure, which we just felt was unethical. It's an invasive procedure. You have a needle put through your uterus into your ovary. There's a syndrome called superovulation syndrome, which is life-threatening in some cases to women. There's a chance of bleeding, and it depletes your eggs. So ethically, we felt that this was totally inappropriate. But we had, my colleague Lyle Armstrong and I had a better idea, which was use cow eggs. Use cow eggs, make cowgirls. Cowboys. Because the argument is, if you take the nucleus out of the egg, and you've removed, let's say, your genetic identity from the egg, and I transfer your DNA into that egg, and it takes on your identity. If I have a cow egg, and I take the nucleus of a cow egg out, it's not a cow anymore. It's nothing. And if I transfer a human cell into the cow egg, it now becomes a human embryo. Yes?
So, why cow and not chimpanzees if they are close to our genetic?
Because cows, we eat thousands of cow eggs a day. Could be cows, could be pigs, could be rabbits. It had been shown to be successful with rabbits.
Right. So there's no difference whatsoever.
But chimpanzees, you're never going to get thousands of eggs. This was a readily available source of eggs. The abattoirs are full of cows getting sacrificed every day. We throw the eggs out.
So if you had a person, obviously you haven't made a person that way.
No, you can't. That's illegal.
Supposing there were lots of people walking around and they signed up for 23andMe and they had their genes analysed and one was their maternal line and it said Frisia. They trace your maternal line by doing your...
Yeah, so you can't, it's illegal almost everywhere in the world to do what's called reproductive cloning. That is to take an embryo created by SCNZ and put it into a uterus, animal or otherwise.
You said almost.
Well, there are some countries, well, in the U.S., for example, you won't believe this, the U.S., where embryonic stem cells are hugely controversial, there are states in the U.S. where you could clone your sister. Seriously. It's not illegal.
Which states?
Mississippi, Idaho, I don't know. There's about 20 states in the U.S. where this could be legal. Yeah.
You mentioned legality, but what's the enforcement mechanism?
So here in the UK, this is really a long, complicated story, and I don't want to get into this too much because it happened, 5-6 years ago. But so we brought this to the regulator. We said, look, if we want to do this, this has to be interpreted as a human embryo. If you say it's not a human embryo, then I don't need a license from the regulator to do it. I can just do it. But Lyle and I, and ultimately a third group from Keith Campbell, we said, this is a human embryo, therefore we're coming to you with a license. The government said they were going to ban it. We're not even going to get it put in a license. The government's going to ban this. The scientific community fought back and said, this is BS. You can't just ban science. So we went to consultation with the Select Committee in the House of Lords and the House of Commons. The HFDA had their own Select Committee, blah, 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 blah. They all agreed that this was a human embryo. And then we got taken to court. And then the big thing that happened was the cardinal. Where is it? The cardinal attack. So then the Department of Health decided that there were going to be all these new classes of embryos and we need a new embryo bill. So we started working with the Department of Health and Don Primarillo and to take a bill through which would now categorize all these embryos. Embryos, half hybrids or cybrids or half human, half cow embryos, whatever you want to call them. And then we were going to take a bill through Parliament, and then the Cardinal came out and accused Gordon Brown of trying to trample on the religious sensitivities of MPs, and we got in a huge brawl with the church, which was not good. Catholic archbishops used Easter sermon to attack embryology bill. In the end, we got the bill through. The scientific community was, heavily engaged in working with Parliament to try to educate them around all of it. Okay, and then, of course, as things happen in science, it all became moot because right at the same time that we get the bill through, somebody comes along with a different way of doing this, which in essence says, if I take 4 genes that control the state of this. Remember I said these cells, you can just expand them forever, right? That's controlled by a set of genes, which we call pluripotency genes. And they're only expressed in embryonic stem cells. They're not expressed in other cell types, except maybe rarely in cancer cells. But a guy named Shinya Yamanaka from Kyoto started taking the genes that are highly overexpressed in these guys and putting them into skin cells. And lo and behold, he found that there's 4 genes that if you put them in a skin cell with a frequency of about 1 in 5,000, I can make what is in essence a cloned stem cell line from any of you simply by overexpressing these 4 genes. And in essence, we think, although it's not definitive, they are no different than stem cell lines that you would make from embryos. They're just made in a different way.
So it's a pluripotential stem cell.
It's exactly, they're all the same in principle. I mean, there are probably some genetic differences here because you're starting out with an adult cell and you're just genetically engineering it to go back. Now, this was revolutionary, and he won the Nobel Prize 2 years ago, which he should have. But it completely put us out of business here. Totally. Yeah.
What about all the mutations that accumulated in that adult cell?
And that's exactly, and that's one thing that we talk about. Interestingly enough, if you take a cell line, if you take a cell like this, where it's had one allele of a very important tumor suppressor gene called p53, it's been knocked out. Which is one of the first things that happens in cancer. The efficiency of making these goes up 100-fold. So what these things are, I don't know. But this has turned into a huge industry. There are now probably 10 or 20,000 of what we call iPS cell lines now that have been made from thousands of people. Many of whom have very rare and interesting genetic disorders, many of which are genetically normal people, as far as we can tell, at least at the time we made the cell lines. Yeah.
What do you think of epigenetics? Because there are certain like diseases you can get, and the genetic mutation's the same, but it depends on whether it comes from the mother or the father. And there's also, they've studied famine, and it's actually affected people genetically.
Oh, yeah.
So that, how does that fit in with your picture of stuff, and where does that extra sort of metadata get tagged?
Yeah, that's a very good question, and one that, you know, I'm not addressing here at all.
Because you said the cow cell will be the same, but of course that only looks at it from a genetic basis. There could be some epigenetic metadata.
Oh, absolutely.
One knows how it's encoded.
You know, and the thing is, when you culture these cells for extended periods of time as well, you're getting epigenetic changes, and you know, people rarely look at. I mean, this is where you're not modifying the DNA, but you're modifying how genes get turned on and off. Okay, so it's like a super level of organization within the genome. You know, and I'm absolutely convinced these things are not the same as what you get from this. That's my own personal bias. I think they're very different, but this is still very useful technology. And the only other thing to say, just one other second, this could be a source of cells for each individual in the world, and we can talk about the costs of that. I know people had already brought up healthcare costs, but this is the plan, is, you know, let's make a cell line from everybody, bank it, and then when you need new heart cells, you need new brain cells, whatever, your cells are sitting in the freezer, and we just have to figure out how to turn them into the appropriate cells. So that's really, in addition to disease modeling, the ability to have you know, your own matched cell line that you can make any cell from is the really big drive for this particular technology. Yeah.
So in most cases, the middle one and the one in the bottom, you zap it with something. So what is that magic thing? You zap it and then it magically converts to something else.
So this gets zapped with electricity.
Electricity, why not ultraviolet or whatever?
It just seems to work. Or you can use calcium. You don't need sperm. And this happens all the time. We have things called parthenoids, which are eggs that just self-activate. Okay, so you know, no men are included in this process. Okay. Yeah.
So is it where it gets tricky, where it fails most of the time?
Oh, this is only recently worked using human eggs. Only in the last 2 years has anybody successfully done this. We never could get funded to do this because once IPS came along, everybody said, you don't need to do cloning anymore. So this is still very, very, very inefficient. Only one group in the world has successfully done this. And one more question.
Why do you need to bank your cells? Why can't you just create them when you need them?
Problem would be is that this process takes a while, and then you have to characterize each. So you end up with a bunch of different clones, and then you have to characterize each one. And so if you came in with acute injury, you know, this wouldn't help you. This will work well for chronic if you want to make it. But what people are thinking is if you already have it banked, pre-banked, and already expanded and characterized, all you have to do is figure out how to differentiate them. And then, you know, in some cases you can differentiate the cells pretty quickly. Okay, let me move on because this was sort of a little sideline. I just want to make sure, because IPS comes up a lot. Everybody talks about IPS, right? And in essence, this is the take-home message. We think all of those different cell populations are roughly the same. Okay, they can all be turned into almost any cell type, whether they're from IPS, whether they're from cloning, or whether they come from an embryo. Right. I don't know, they really got into the cows for some reason. There was a headline in the Sun that said mutants, which showed a guy with a cow head and a briefcase, which I thought was quite good. All right, let me show you now, I'll show you a bunch of different ways that we're using these cells, because I'm almost conscious of the time. So, 5.5 years ago when I joined GE decided we were going to be a human embryonic stem cell company. Now that's pretty bold for an American company where embryonic stem cells are really, really controversial. I mean, Bush banned the whole field for a number of years, and then Clinton let it back in, and then when Obama became president, there was a lawsuit against the federal government that banned everything again, and it was only about 3 years ago that that ban has now come back out. The Supreme Court turned it down. So now most American researchers use IPS cells because there are still 20 states in the US that even if you have federal money to do embryonic stem cell work, you're banned in that state from doing it, okay? So for GE to come out publicly and say we want to be an embryonic stem cell company was, in the US at least, very, very controversial. But there was a good reason for that. As I said, we wanted to use human cells to generate better, more predictive models for how safe and efficacious drugs might be that are going through development. The first thing to point out is that every year there are a number of compounds or biologics that go through the whole drug discovery process, which in general takes about 12 to 15 years per drug, at a cost of between $1 to $5 billion per drug, where the drugs go all the way through preclinical development. They get tested in animals, they go through phase 1, phase 2, phase 3, licensed by the FDA, go out into general circulation, and they cause, in this case, significant cardiotoxicity. And those drugs get withdrawn. Okay? To give you an example of how really bad this is, anybody recognize this compound? Vioxx. Vioxx killed over 25,000 people by fatal arrhythmias. Was never detected at any time during development. So that cost them about $3 billion Merck in development costs. The lawsuits to date with the US Justice Department are on the order of $8 billion. You want to know why drugs are so expensive? Every time one of these guys fails, it gets tacked onto the next drug going through development. Pharma cannot afford this anymore. They're in complete and total meltdown as it is, and having drugs that fail in late phase 3 or after they've been approved is just, it just can't happen anymore. So, pay attention to trofinidine and cisapride. Why do these drugs fail? They fail because the tools that they're using to assess potential toxicity rely almost exclusively on animals and animal preparations. And pharma's been doing this for 50 years now, and they still have drugs that fail every year. You would have thought they would learn, but they haven't. So that was the motivation for us to get into this field, because of our long-standing collaboration with pharma companies. They came to us and said, you think you can come up with something better, because we can't deal with this anymore. So the idea was to take human embryonic stem cells, these cells that we can grow forever, not IPS cells, not clone cells, embryonic stem cells from embryos, and basically figure out how to take them in their undifferentiated pluripotent state and turn them into really nice human heart cells, with the hope that these cells will be more predictive and more informative than animal preparations. Okay? So this is one of the reasons why I was hired to join GE, because we had a lot of experience with embryonic stem cells. And back in 2009, this was still a relatively nascent field. So, together with a company called Geron, which was the first group in the world to get FDA approval to take an embryonic stem cell derived therapy to the clinic, we set out to do this. And basically what we did is we came up with a protocol that takes cells that want to turn into everything and basically sequentially takes them through the development of a heart in utero, and you end up with adult human heart cells at the end. Okay? It takes about 28 days. There's no genetic manipulation, there's no selection. This is just literally taking them through embryonic cardiac development. And I'll show you that in a moment. And then for each, we make, and we do this at an industrial scale. I mean, 5 billion of these cells is a lot of work. Okay, I've got probably 15, every time we do this, it's about 15 people continuously working for 30 days to do this. And on the day we harvest, it takes a whole day of 30 people to harvest because we end up, with about 3 to 4 billion cells. Okay, so this is like mass production. Okay, and then for each of these batches of cells, we'll characterize them pretty extensively, particularly looking at their functional attributes, and I'll show you that now. To give you an idea of what this looks like, this is on day 28 at the end. Basically, this is your heart sitting in a dish beating. We're not stimulating this at all. This is purely spontaneous. So what you have to imagine is you've got 40 flasks of cells about that big, and all of them have a contiguous sheet of contractile myocardium. And they beat in synchrony because they have all the cells that you have in your heart, including the nodal cells, which pace the whole population. So as you can see, they're all beating together. They're not beating spontaneously here and there. Okay. What else do I want to say? They beat about 70 beats a minute, which is probably for most of you what your hearts are beating at. If these were fetal, they'd be beating about 120, 140. Okay. Surprisingly enough, when we harvest these, we use enzymes to dissociate this whole mass down to single cells. And we freeze them in liquid nitrogen, ship them all over the world, and when you get them, you just thaw them, plate them back out, they reform, what we call the syncytia, they become electrically coupled again, and within about 3 days they start beating. Okay, so we can mass produce these cells as often as we want and ship them to Australia, to Japan, to California, and we do this routinely. Yeah?
So, did you consider also mass producing hepatocytes?
Yes.
And then in toxicology testing, first expose the drug to hepatocytes, then take all the metabolites and put them into cardiocytes?
That's what we had proposed to do down the road. So he's asking about making liver cells. We can make heart cells, can we make liver cells? And the bottom line is no. Making liver cells is much, much more complicated than making heart cells. We all can make liver cells, but they're incredibly immature. They're very fetal-like, and we don't think they're predictive at this point in time.
So a toxic metabolite can still slip through?
Yeah, but we're specifically screening for cardiac. Yeah.
But, there is a story that the 2D, two-dimensional...
It works for this. I'll show you.
Because that
I'll show you.
Research for 3D printing coming into...
Yeah. Don't worry about it. Don't worry about it. For cardiac, 2D works fine. And I'll show you.
Yeah.
I'll show you
about the liver, you said.
Yeah, the liver. We've tried that. That doesn't push them toward an adult phenotype. It's not the three-dimensionality, it's what genes are turned on and which genes aren't. So they're still locked in a very fetal state. And my suggestion has been expose them to children and maybe a bit of Jack Daniels, and maybe that will make them. But to date, that hasn't been enough either. Now I'm thinking maybe cigarette smoke or bad music or something. I don't know. Liver has been really complicated, and none of us really understand why. Neither us, our competitors, or the academic groups that work on liver developments. It's proved really difficult.
In someone that's had a heart attack and lost some cardiac myocytes, can you infuse these in, or do they not engraft?
In the studies that have been done to date, they engraft very poorly. They don't survive very well, and they don't integrate into the normal beat pattern of the heart. But when I talk about some stuff at the end, you'll see why we've decided to focus on heart. So hang on to that thought. This is really one more question.
Okay, so in clinical trial, you basically try on different people, let's say.
Yeah.
Here you have an extract from some person, and you grow some heart cells out of that person, and then you test.
Hold your disbelief for 5 minutes, okay?
Okay.
So they look like heart cells, and we've compared them side by side with cells that we've taken from cadaveric heart, okay? Now, the data I'm going to show you now is from some of the first cells we ever made, back in early 2010. These were not the best cells we ever made, but we didn't have the ability to test them internally, so we shipped them off to the US, this company called Chantest, who's a contract research organization that does cardiac screening for pharma companies. And what they showed is cells, cardiac cells, their sine qua non is that they're electrically active. You know, their firing action potential is just like brain cells, although different, but they need this kind of ionic machinery to be able to contract. Okay, and Chantes looked at about 125 cells where they individually patch clamped them, stuck an electrode into them, and what they showed is about 80% of the cells are from the ventricle, and they have this very unique action potential pattern that lasts about 350 seconds. Okay. I'll try to keep this really simple, but you'll see how powerful these cells really are. About 18% of the cells come from the atrium, and about 1 to 2% are nodal, and they're the pacemaker cells. If I were to take your heart, digest it down, and do the same kind of analysis, you are roughly 80% ventricle, 18% atrium, and 1 to 2% node. That's why we think what we're doing is actually taking these through a developmental program that mimics what happens when the heart's developing in utero in the baby. Because you end up with the same thing at the end. Okay, isn't that cool? I mean, everybody used to say, let's use human stem cells as a tool for understanding human development. And I always thought, well, that sounds really good. What does it mean? And this is exactly what it means. And now people have done this with other tissues as well. So, they look like heart cells, they act like heart cells, they've got all the capability electrically of heart cells. Are they useful? They must be, because I wouldn't be telling you this is there. So, this is a little bit complicated, but I want to try to make it crystal clear, and if I don't do a good job, you can yell at me. Okay, these are ventricular cells. And ventricular cells have this unique electrochemical property where they sit down here at a really low resting membrane potential, and then when they contract, or when they want to contract, they fire an action potential. You see this really sharp increase in membrane potential, and then this very rapid decline back down to where they started from. So basically, this controls the contraction. And the cells have to get back down here in about 400 milliseconds in order to be ready to contract when the node fires and to contract in synchrony with the atrium. Okay? Does that make sense? If they don't, you're basically developing an arrhythmia. Because your node's firing, your atrium's firing, and the ventricle is not. Ventricular cells express a unique potassium channel called hERG. That's important in getting the cells back down here in the appropriate time frame. And some classic, what are called hERG channel blockers or pro-arrhythmic drugs, what they do is non-selectively, they weren't intended for this, it's an off-target effect. I mean, when you think about Vioxx was an NSAID, it was a non-steroidal anti-inflammatory, and yet it somehow binds to hERG. It has no functional reason to do so, but it does. And when these compounds bind to hERG, in a dose-dependent fashion, they delay ventricular cells from getting back to their resting membrane potential. So you can see this cell sitting out here is way off, okay? Way off, and the node's fired, the atrium's fired, and maybe 200 milliseconds later it fires. So this is a pro-arrhythmic drug. This drug was marketed in the US as Seldane. It's an antihistamine, and it's a really great antihistamine because it doesn't make you drowsy. I took this drug and it gives you arrhythmias. Now, this is when I was doing my postdoc, and my postdoc boss was a little bit of a nightmare. So I thought it was him and not the drug. But, I'm on Holter monitors and all this stuff, and finally the guy said, I don't know what's going on with your heart, it's all over the place. And it's a really uncomfortable feeling to have arrhythmias. I don't know if any of you have had it. It feels like your heart's just bouncing around all over the place. And when I came off of Seldane, it disappeared. So if you look at cisapride, you can see exactly the same thing. In a dose-dependent fashion, these cells are not getting back down here when they should. And at an even higher concentration, you're starting to get something that's really abnormal, right? And then this compound, which thank the Lord never got approved, is probably the most pro-arrhythmic drug ever made by Eisai. And I met the guy who actually synthesized this compound. And I can't remember what the clinical use was, but you can see at a high concentration, it completely disorganizes the heart. So this drug would kill you if you took it.
Is it now tested as a weapon?
It is the standard drug that people use in comparative. If this drug doesn't work on your preparation, you got a problem with your assay. Now, when I saw this data, I was flabbergasted, because these are some of the first cells we ever made, and already with some of the worst cells we probably ever made, I could have told these two drug manufacturers, you got a drug that's pro-arrhythmic. With the first cells we ever made, why weren't these compounds picked up? if this is so predictive, so indicative of a drug that's got a problem. And the reason is we're not animals, we're human. So Chantest did this test where they compared our cells to these two standard preparations that pharma has used for 50 years. They're called Purkinje fibers, which are microdissected either from the rabbit or from the dog. If we just focus on Celdane, we showed that we could detect this pro-arrhythmic activity at a concentration of drug that I would take, or that you would take. With the rabbit, you'd have to give the rabbit 35 times more compound than you would ever put into man to get the same response. And the dog, even at 100 times more compound than any of us would ever take, the dog says this drug's perfectly safe. We're not dogs, we're not rabbits, we're not mice, we're not rats, we're human. And humans respond very differently to these herd channel blockers than animal preparations do. And the same thing is true of cisapride. You need 10 times more drug. This data was published in 2010. We took this data to the FDA in November 2011, and they got it completely. They said, get rid of this. And we're working with them to make human-derived heart cells, either from iPS or from ES cells, the standard for the way that drugs should be assessed for safety. And if we had hepatocytes, to this gentleman's point, we'd be doing this with hepatocytes as well. Okay? So in really less than a year and a half, we had already convinced the FDA of the validity of this. Now this is really hard because you can imagine the FDA is really conservative. They're not open to change, and the pharma companies are even less open to change. So getting the FDA to agree to this was really quite surprising. So we and our competitors, several pharma companies, and the FDA are part of an organization called HESI, which we're using to make this the standard for how drugs should be assessed. Okay.
So then, if once this becomes best practice or law, are we talking about a future where drugs in development will fail quicker?
Yeah. So that's a very, very good point. That's the general idea. You screen them really early because compounds, that fail here, they've lost life. Even if they fail at phase 3, you've already spent $1 billion. So the idea is you screen really early, and maybe you screen your whole compound library for efficacy and safety at the very beginning. So the idea is to get rid of potentially protoxic drugs very quickly. Yep.
Are you still screening against one person though,
yep,
unless you're using a range of lines?
Yep.
And so.
Yep. Now that's the plan, is to use a lot of lines, but in this type of assay, in the assay I'll show you in a moment, we've never gotten false positives and we've never gotten false negatives. And we've nailed every drug that's shown clinical toxicity. So it may be important, I think it'll be particularly important in looking at hepatotoxicity, where the metabolic activity of the drug is going to be crucial. And different ethnicities will likely metabolize drugs very differently. One more question, because I'm never going to get done.
Maybe this is a really stupid question, but you said for 40 years they've been testing on animals, but couldn't people that donate their bodies to science, couldn't you extract their cells and use them?
Yeah, the problem is cardiac cells are notoriously terrible from cadaveric organs. I mean, people have tried to use human heart cells, and they're just awful. I mean, we bought in a couple of batches, and they were just terrible. So, it's probably no better than this. Okay, I haven't even gotten to cell therapy yet, so I'm going to speed up a little bit. Okay, so that was what we did with the FDA on drugs that cause electrical toxicity. Okay, there's a whole class of compounds that are very different, and this data really the FDA did not like at all, but it's also made them change the way they think. And it relies on what's called high content imaging. Believe it or not, these are microscopes. Okay? Except they don't have oculars or anything. So they're very, very powerful microscopes in a box. They're designed for high throughput screening. We have pharma companies that, you have a plate of cells that has either 384 or 1,536 little wells, and they'll do 100 of those a day. Okay, I mean, these are designed for really, really high speed, very accurate assessment of cells. Not only do you get very nice color pictures of cells, but embedded within the image, you can ask the machine to give you as much data about each and every cell that you want. How big's the cell? How many mitochondria? How big's the nucleus? How many neurites does it have? And all that data is embedded in the cells. Now, this is not unique to GE. Either Salomics has one, PerkinElmer has one, but they're all designed to acquire just massive amounts of data about cells, not just pretty pictures, but the data inherent within them. So to give you an example of that, this was a. Can we turn the lights off for just a second? Is that possible?
Might be on the control panel.
Oh yeah. Nice pictures, huh? So these are actually live cells that we've stained with some dyes, and these are our human cardiomyocytes. So I know that this is a heart cell because this red dye labels the mitochondria, which are like the batteries in the cells, and because remember cardiomyocytes are contracting, they need a lot of energy, okay? Blue is the nucleus of the cell. That tells us if it's blue, that the cell's alive, and green is just showing us how much calcium is around. So that's in a healthy, nice, happy cell. Now you hit it with a cardiotoxic drug called amiodarone, which is still used clinically, although everybody knows it's very cardiotoxic. And look at how the cells have changed. All the mitochondria have shriveled up. The nucleus has lost that really nice bright blue color. You know, these cells look like death. They look very, very bad. Okay, now we can go back, David, to lights. Okay, so what InCell can do is it can measure the change in the mitochondria. How many mitochondria are there, its shape, its size, all that kind of stuff. And so you can collect all this data. So you're now not only getting look at a cell, but you're starting to get a lot of data about what's happening inside the cell. So my colleague Nick, who just retired after 35 years at GE, probably the smartest scientist I ever met, presented this data at a meeting in the US in 2010, and it got a lot of attention, and particularly we got a lot of attention from a group of guys at Genentech in San Francisco. Genentech has a big problem. They are predominantly an oncology company. They're predominantly making drugs for cancer. And in this study that came out in Nature Biotech a couple of years ago, if you look at all these different clinical indications, all of them roughly start out with the same number of drugs, have the same number of drugs that fail, and get the same number of drugs roughly to the clinic. But look up here. Something like 90% of oncology drugs fail because they're cardiotoxic. So the attrition rate is huge. The problem is the toxicity isn't what I showed you just a minute ago in terms of it binding to her. This toxicity is completely different. And there have not been good assays for this except putting these drugs into people. Okay? So if you screen them against her, they're clean. And if you put them in animal models, they're clean. And then you take them to the clinic and people start having a whole range of heart abnormalities. But it's not related to electrical imbalances in the heart. It's something very different. So our pals at Genentech said, hey, we think that this might be this type of assay, which is looking at cardiotoxicity structurally, might be a really good assay for us. But we had to validate this. So the guys at Genentech sent us 26 compounds in the post to Cardiff. The guys in Cardiff tested them. So 7 doses of each compound in a clinically relevant therapeutic dosing range. We looked at different times of exposure. We did the staining that I just showed you, and then we looked at 19 different things within the cells to see if we could detect problems. So the data set is massive. It was like a terabyte of data. It was huge. And when you put up all the data, it doesn't make any sense at all. So Nick came up with this very little interesting graph, which I hope is simple enough, because it's simple enough for me that you'll understand this. Basically what he's done is he's taken all these measurements of the battery in the cell down here. So these are the things that, if you start to impact on the mitochondria, you're going to kill the cell. Okay? This is the levels of calcium, which might be important in that you're damaging the cell over a long period of time before you kill it. And then lastly, this just tells you how many cells are alive. So the drug that I just showed you, the really nasty one, is down here, and you can see that compared to this drug, which is very safe and it's used clinically all the time, mitochondria are nice and happy up here, and the cells are all alive. When you use amiodarone, you can see that the mitochondria just get wiped out, and not surprisingly, the cell gets wiped out. Okay? So those are the 2 patterns. That's all you need to know about this. Happy cells, happy mitochondria. Dead cells, dead mitochondria. Okay? Now, when we did this study, we had no idea what these compounds were. At the time, we didn't even know they were oncology drugs. So all the data I'm going to show you now is after we unmasked it. And you can use that little pattern I showed you to start to make some very interesting conclusions about things. So these are 6 clinically used tyrosine kinase inhibitors. Most cancer drugs are kinase inhibitors that recognize a whole bunch of different kinases. And kinases are the signaling pathways in your cells. And in cancers, they're almost always mutated and almost always out of control. And they control cell proliferation, okay? These happen to be tyrosine kinase inhibitors, but there are ERK kinase inhibitors, MET kinase, and there's a whole ton of different kinases. Most major oncology drugs target them because it's a way of dampening down proliferation in cancer cells. Okay, so these are all used clinically and they're all important. You might recognize this one because it's also referred to as Gleevec. And you can see at the lowest dose, these all look like the nice happy mitochondria and happy cells. You increase the dose to the next one, nothing much changes. Now look here, at 11, these 2 compounds flip. Instead of nice happy mitochondria, now the mitochondria are getting destroyed, the cells are getting destroyed as well, and when you increase that to 33, it's exacerbated. And at 33, Gleevec shows that same pattern. So what this shows you is that not all tyrosine kinase inhibitors are cardiotoxic, even at the highest dose, and that there are dose-dependent effects of these 3. Okay? And this is highly reproducible. We've done this assay over and over again. And then I won't dwell on this, but you can start to see some other little interesting idiosyncrasies, like here's a compound, it's against a different kinase, and this looks just like the fetapine. All the mitochondria are really happy, but now all of a sudden you've got this worrisome increase in calcium. Cells don't like high levels of calcium because it starts to activate a whole bunch of cell death programs. This hasn't happened to any great extent yet, but maybe if you expose the cells for another day or 2, you see viability just plummet. Okay? If this is my compound, I'm really concerned about this. It's not overtly cardiotoxic, but there's something weird going on here. If you look at this compound, you see the same thing, but now you're starting to see loss of mitochondria. Okay? And if you look at Gleevec on its own, the mitochondria just get wiped out. There's a huge increase in calcium, so this is cell death activation, and it kills the cells. Again, this was all done blinded. At the end of the study, when we unblinded, you have all these compounds which are absolutely safe, with the exception of some where we're starting to see this increase in calcium, but no overt cell death. And then a group of compounds down here which are all clinically uniformly cardiotoxic. Now, I've presented this data to almost every major pharma company in the world, and they don't like this at all. As you can well imagine, because in their hands, they didn't see this. Because they didn't do this kind of assay. Nobody had. This is brand new. They looked at animal models, and they looked at in vivo animal tox, and they didn't see anything. The FDA also did not like this data at all because they approved all these compounds and only discovered that they were cardiotoxic once they were in the clinic. So they didn't like this data at all. I mean, this discussion lasted for several hours, and they said, look, we've never seen this data before because we get hERG data and we get in vivo tox data. Now this is something completely new. You know, come back to us and validate that. So we went back with Genentech. This data is under review at the moment, so I'm not going to show you any of it. But we looked at another 110 additional oncology drugs. We came up with exactly the same thing. Where there was overt clinical cardiotoxicity, we picked it up with ourselves. Where the compounds had never been shown to be cardiotoxic, we saw nothing. So now out of a total of, and together with collaborators and other pharma companies, we probably have looked at over 500 compounds now. The cells have been absolutely predictive, both in looking at hERG and then looking at the structural toxicity. In addition to doing this kind of high content imaging, we looked at gene expression, we looked at bioinformatics, we looked at bioenergetics, we looked at metabolomics, we looked at biomarkers. We even looked at the influence of anaerobic versus aerobic metabolism, and we found compounds that were only cardiotoxic under anaerobic conditions and not under aerobic conditions. The bottom line is the amount of data we presented to the FDA was so exhaustive, they said, okay, we get it, we take it. So now again, we're working to make this something else pharma will have to do to show safety of their compounds over and above the electrical activity in the heart.
What's the additional cost of adding one extra test for one new compound?
Don't know.
You don't know?
Don't know. Compared to $2 billion, Not
Yeah,
much.
but I'm just wondering
a few
whether-
thousand, few tens of thousands of dollars.
So I mean, I'm just wondering whether the concept at some point in the future would be to just screen every single thing in the world, you know, not even compound, just like, you know, everything that you might come into contact with or something like that.
That's what I mean, well, you know, so like there's a big move afoot in the U.S. now to screen 6,000 industrial products.
Okay.
There's a big thing on, cosmetic screening. You know, instead of doing it on rabbits and doing nasty stuff into rabbits' eyes, you now do it on cells. EPA has a big program on this in the U.S. as well. So, you know, what we tried to say to pharma is, you know, when you're screening your 10,000 compound library and you're looking for hits, why not screen for hits and safety at the same time, rather than, you know, coming up with a whole bunch of hits that then prove to be toxic and then you have to turn around and go back. So, yeah.
Two very related things. One is, you know, a lot of drugs get developed and then they get used for a completely different purpose. Like, for example, that's how Viagra came around. And related, does it get to a point where you can so accurately model the body or the effect on every single cell, you could develop new drugs just by randomized testing? Because let's say you have 100 million tests and you want to kill a particular, you know, type of cell, a cancer cell or whatever, so you want it to have a certain effect on the body, you don't want it to have several million other side effects. You just try so many combinations that you just get the drug by no engineering, just by pure mathematics.
Yeah, so I mean, the idea is in the future you'll have 20 or 30 different cell types, and you'll probably have them, as this gentleman was alluding to, you probably have them in some sort of microfluidic device where, you know, it's not just the drug, but it's the metabolites of the drugs, and maybe things that other cells are secreting in response to the drugs. So there's this whole thing called body on a chip that people are trying to develop, you know, when we can make all of the relevant cell types. And so then you may just screen everything, and, you know, and
the result pops out.
Yeah, it's probably, it doesn't sound very advanced, but it's probably no worse than the other way that pharma screens for compounds, I would guess. One more question, then I'm going to move on to therapy.
It's all about drugs right now. What about physical hackers?
Like?
In crude terms, putting a mobile phone next to yourselves and then finding negative effects, being shot by a sniper, fired by
I mean, environmental factors, I agree, definitely. Okay, so I'm going to move on very quickly now because we're getting to the good stuff. I just wanted to show you a way that most people don't think about cells, which is also going to have huge health benefit, you know? So the plan is, you know, we'll make a whole bunch of other cell types. This is ongoing. We spent a lot of time on hepatocytes, and it's really frustrating. But the plan is to bring up in about 100 different cell lines from all over the world. So India, China, Korea, Japan, South America, Norway, Middle East, etc. Now that presents problems for us because we're already maxed out, to put it mildly. And, you know, I don't know how many people I'm going to have to get, how many incubators I'm going to have, and how many, you know, tissue culture hoods. So we're going to need automation, and we're going to need mass production on a scale that's really pretty hard to imagine. But this guy might help. So this is how you grow cells in the future. So this is Motoman. He's a very expensive next generation Japanese robot. He's got the most advanced hand in the world. He's got something like an 8-joint arm hand. He's about $1 million. But the great thing about Motoman is most of us would like to grow our cells in 3% oxygen, which is about the oxygen tension within your body, and it's 21% in the air. Okay, so Motoman could work in 2% oxygen, no problem, right? And he works 24 hours a day, 7 days a week. Doesn't come in hungover. Doesn't have to go have a cigarette and leaves his cell sitting out on the side here. Doesn't, sulk around for a week when his girlfriend leaves and all that kind of stuff. So a much more reliable and dependable way to grow cells. The only problem is he's not scalable either. So the whole thing would have to be in like a Wembley stadium of incubators and hoods and stuff. So although I thought he was pretty cool, he's not the solution to the problem. But we'll come back to that. So scale up of production facilities for this is a really huge problem and something we're trying very, very hard to address. But it's the same problem that we have with cell-based therapies. Many of the things that we want to do, if I'm going to grow human embryonic stem cells and turn them into cardiac cells to put into people's hearts, and I'm going to, I want to grow enough cells to treat 10,000 or 100,000 patients, that's going to be a lot of cells. And you cannot do it in traditional tissue culture cell growing. So when we got into this 5 years ago, we spent a lot of time thinking about, well, what's the workflow look like? You know, I take a cell, whether it's from bone marrow, from adipose, embryonic stem cells, iPS cells, I've got to scale it up. Different cells are going to have different requirements. Some of them can grow in suspension, some of them have to grow on a defined substrate, some need extracellular matrix, some like MSCs can grow on plastic. You know, every cell is going to be different. Some can grow really at high density, others are very, like ES cells, are very nervous about growing at high density. You know, then you're going to have to convince the FDA that your cells post-expansion have not fundamentally changed from before. They're still safe, they still will be the cells that you want to use, and that they don't raise any safety concerns. How do you get the cells in? Imagine trying to inject cells into the heart. So you go through the the femoral artery, up into the left ventricle, and you've now got your injector, except the heart's moving. You know, so imagine trying to inject in something that's beating 70, 80, 90 times a minute. Okay? If I put cells into the brain, we've done a lot of work in the brain. The problem with the brain is under hydrostatic pressure, so no matter how careful you are and how slow you are about injecting cells, the minute you pull the needle out, cells go up the needle track and lay on top of the brain, in between the brain and the dura. They don't do very much good up there, they need to be in the brain. So we've got a whole bunch of problems around administration as well. And then as I'll show you at the end, being able to track cells that you've either injected, infused, or you've stimulated, endogenous stem cells, using diagnostic imaging would be really, really important. And yet, at the moment, we can't do it at all. Okay? So now I'm taking you a little bit farther into the future. So, there's a whole bunch of different technologies that are available. This is one that we bought a few years ago. It's a company in Boston called Accelerex. And these are big bioreactors. They're for growing cells. Okay? The difference is, if you notice, up here at the top, this is all plastic. All the lines are plastic. Everything's plastic. This is just basically a big vessel to hold the bag in. Which means this is all single-use and disposable. So 1 week I can be growing cells, 1 week I could grow virus, next week I could grow monoclonal antibodies, and I just strip all this out, throw it away, put new stuff in. This is about a third of the price of conventional bioreactor, bioprocess, and it's really fast. There's one problem with this picture though. Not expensive. It's actually fairly cost effective compared to, you know, if you've got an army of people. So let's say this is a 500-liter bioreactor. Okay? Compare that to the number of people you would need to grow 500 liters of cells in a lab. So it's very cost effective.
The amount, what to be?
It's the carbon sources. Got to get those guys out of there. People are the worst thing about growing cells. You want no people involved, and I'll show you why in a moment. People are buggy. We're covered in bugs. Remember I said we're 90% bacteria. You don't want bacteria in here. Okay? Mycoplasma, E. coli, Sibillus, you name it, you got it. It's everywhere. Okay? And people are inattentive. They're lazy. They're inconsistent. So you want everything automated. You want everything closed. You want the cells going in, these guys out of there, computers doing all the work. You harvest the cells at the end, again, all done in automated fashion. The cells show up in a vial or a syringe, and they go into the patient. So no people, completely closed and automated is the mantra here. Now, so this is this would be useful if you're going to grow cells on a really large scale. You know, I'm going to grow, I don't know, 10,000 lots of cells in one single batch, characterize the whole batch, ship it all over the world, come back a month later and do it again. But for a lot of the technologies we're talking about, so this is called allogeneic. A lot of the clinical applications we're talking about are autologous. I'm taking your cells out and then putting them back in after some manipulation or expansion, right? So I'll take you through this again, but it's something called immunotherapy, where in essence you're taking a small girl, you're harvesting cells from her, and then you're going to put them back. And for her, she needs a reasonable amount of cells. So this would be equivalent to one technician in the lab. Maybe it would take them half a day. Okay? Now, if you start to go up to larger folks, this spirals out of control very quickly. Now imagine you're doing 10 or 20 patients a week. Okay? Secondly, what's the problem with this is that it's open. And my buggy friends who are inconsistent are going to contaminate these cells. Almost certainly. No matter how good they are, how clean the room is, this is a disaster waiting to happen. So what we did is we kind of pioneered taking some of that single-use idea, although this predates that, to come up with closed bioreactors that are automated and perfusion-based, where you don't have somebody actually physically doing any work. Okay? So this is called Zuri. It used to be called Wave. And basically what you do is this is a rocking platform. That's why it used to be called the Wave, because you kind of get this Malibu effect of the media kind of rolling around inside. So you hook this up to a CO2 source so you can drive the oxygen tension down. And you hook it up to a bottle of food. You pop your cells in here. You hit the button. It starts rocking. It's heated. Doesn't need an incubator. And you go to the beach. You come back in 2 weeks and you harvest your cells. And I'm not being facetious. It's exactly what happened. So this is work we did right as I joined GE. So these are for growing white blood cells called T cells. And I'm going to show you, this is proved to be incredibly important. So you take T cells over here, you activate them to get them to proliferate. You put them into Zuri, you hit the button, the machine starts to add juice in, and ever increasingly it adds more and more juice until the end. You come back from the beach, you harvest. Okay? No people involved. You sit on the beach with your computer and you're watching all this happen. Okay? So, we've shown that this is a really stable system. The only thing that changes over time is cell number goes up, but all the metabolites, all the waste products stay very, very low. And in terms of T cells, if you look at what goes in and what comes out is better than what goes in, because you're switching from predominantly a CD4 population to CD8. CD8 cells are extremely cytotoxic. So if you're using these in any kind of treatment where you want to target and kill things, this is perfect. Okay? It is even better in that if you look at whether the T cells become lazy, dull, and boring, or they stay really nasty and able to home and to migrate and to kill. As you can see in dark blue, the cells retain that nasty, horrible killer phenotype. And even at the level of looking at what they actually secrete, the cells are secreting buckets of this stuff compared to this. This is what kills cancer cells. Okay? Tumor necrosis factor, interferon are killer molecules that when they find cancer will absolutely destroy it. And the problem is you almost kill the patient in the process. Where this has become incredibly important, and where almost everybody in the world is using our bioreactors, is in this whole new way of treating cancer called targeted immunotherapy. Okay? I've never seen anything in science like this before. 5 years ago, it's almost 6 years ago now when I joined GE, nobody was doing this except one group at National Cancer Institute and a guy named Steve Rosenberg's lab. And he had been trying to train the immune system to target melanoma for years. Got very inconsistent results. Would have occasional patient with 25 or 30 tumors, would take their cells out, put them back in, complete eradication. Have other patients, same tumor load, same cells, same activity in the dish, put the cells back in, patient dies 2 weeks later, doesn't do anything. Okay? But Steve just kept persevering. He got all these other guys interested. And now, about 2.5 years ago, Carl June's group at Penn reported on a phase 1 safety trial. So this was not designed to show that this would do anything. It's designed to show that modified T cells would not kill the patient. Okay? 5 patients, all in-stage B-cell lymphoma, including Emma. The cells are taken out of the patient. They are genetically engineered to express a receptor for a protein that's only found, in this case, on B-cell lymphoma. Grown up in our bioreactor, put back into the patients. Of the 5 patients, including Emma, 4 went into complete and total remission. This is in-stage disease that has failed all conventional therapy. Emma was probably a week from dying. I mean, I've never seen a child look so bad. At the time she got infused, she was emaciated, she lost all of her teeth, all of her hair, jaundice, looked like death warmed over. And 4 or 5 days later, her lymphoma was completely eradicated. She just celebrated her 2nd birthday tumor-free, her 2nd year of being tumor-free. And by all, every test under the sun, including quantitative PCR, She's got no B cells left whatsoever. This gentleman exactly the same. Now, the problem with both of them is they almost got killed by the therapy. Remember I said these things secrete a lot of really nasty cytolytic stuff, and it drives all of the patients back into intensive care, and they have to go back on life support because they end up in what's called a cytokine storm. The cells are so active and they secrete so much stuff that if you don't treat the patients dramatically, they'll die. Okay? So the cure almost kills you in the process. So on the basis of a single phase 1 trial, Novartis has licensed the technology from Carl and Bruce and is investing hundreds of millions of dollars in building a facility, first in New Jersey and then several other facilities in the world, where they will basically take the same protocol, take T cells out, genetically engineer them, put them back into the patient. This is Michel Sandelin's group at Sloan Kettering, who we also work with. Michel and his group have even more convincing data. 14 out of 16 patients with the same disease, complete and total remission. No B cells left whatsoever. This is now caught on like wildfire. The latest composite study of about 10 or 15 groups all doing B-cell lymphoma suggests that 80% of these patients go into complete and total remission. There is no other cancer treatment in the world where patients go into complete and total remission except following bone marrow transplantation. I mean, this is fundamentally going to change the way we treat cancer. And it's, growing cells in a baggie, in essence. Now the big challenge, this has all been done in what are called liquid tumors, lymphomas and leukemias, where when you inject the cells, they see the tumor immediately, right? And they just go for it. And we're now looking at trying to spin this out into prostate, into breast, into other forms of cancer, where now the cells have got to find the tumor, because unlikely you're going to be able to inject directly into it. You're going to have to find the tumor, it's going to have to evade all the immunity responses that tumors secrete to dampen down T cells in the first place, and they've actually got to penetrate the stroma around the tumor to actually gain access. So I think this is like the honeymoon, and this really works, and there's nothing else like it. But when you start going after solid tumors, I think it's going to be a lot more challenging. But nevertheless, I've never seen anything in science that's just gone on board so fast in such a short period of time, all based on phase 1 data. And now every pharma company in the world is in this. GSK is working with Adaptimmune here, Amgen, Pfizer, Novartis, J&J, Celgene, every major pharma company now has an immunotherapy program. It's just come out of nowhere. Yeah.
The other, I don't know if this complements it or is competes with it or is different, but the other thought is nanobots delivering the drugs, so you get, say, 100 or 1,000 times more targeted.
Yeah.
Does that play along with this, or is that a competing way of treating it?
It might be. It might be complementary, but nanobots are not in the clinic yet. So I've got a colleague in Israel who's using robots to deliver, and in cockroach models they work really, really great. I'd show you that data, but unfortunately I don't have it with me. But it's very cool. The other thing is there's a whole range of new biologics called checkpoint inhibitors, where in melanoma you're getting 70-80% reduction in tumor load, which again nobody has ever seen before. So now we're thinking, T cells and checkpoint inhibitors together, you may get even bigger responses. But that's a really good question. Yeah.
So you talked about cancer stem cells a while back. How do you make sure that while you're doing your big bang culture, you haven't got one cell that's gone rogue and has become a cancer stem cell, and you replace one cancer with another cancer?
Yeah, so these are not stem cells. So these are differentiated white blood cells that we take out and we activate to make them proliferate. And unless you had a really malignant T cell, these things die off after a while, like every other cell in your body.
Presumably the FDA is going to want pretty strong checks on exactly what you've done with those cells, right?
Oh yeah, absolutely. The release criteria for this, that's why I showed you that data. That's how you would qualify your product in terms of its release. But the FDA is giving expedited approval to many of these guys based on phase 1 data, simply because the data is so overwhelming. And they've done that on the checkpoint inhibitors as well. This type of immune-mediated response against cancer is just come out of nowhere, and it's just mind-boggling. The responses that we're seeing are just nothing that you ever see.
What about AIDS? It looks like an obvious target.
So in people who have AIDS or don't have AIDS?
People who have AIDS.
People who have AIDS, there's a couple of approaches. Calimmune and Sangamo are both basically taking out either T cells or taking out bone marrow stem cells, blood stem cells, and genetically engineering them to put in. There's a group of people who have been exposed to HIV who have never been infected, and yet they have antibodies against HIV. So we know they've been exposed, and they appear to have on the receptor that allows HIV to get into T cells, which is that's why it's an autoimmune disease, because it's an acquired immunodeficiency because you lose your T cells because they're infected. There appears to be a natural variant of the receptor where HIV can't get in. And so what Sangamo and Calamine are doing is taking out, in patients who are already HIV positive but on antiretrovirals, you take out their T cells, you engineer them to put this variant in, you wipe out as many of their T cells as you can, you put back the new ones, and slowly but surely you titrate out the virus because the new cells cannot be infected. So in people who are HIV positive, this is the approach.
Stephen, keeping an eye on the time.
Yep.
How close are you to the blue skies? I mean, this seems,
right now.
This seems pretty blue skies.
Oh no, you haven't seen anything yet. Okay, so moving on. Yep, I'll try to wrap up in the next 5 minutes, and then that leaves us 10 minutes or more for discussion. So our kind of plan at GE is I've shown you work on immune cells. I've shown you stuff on ES and iPS cells. We have programs basically to develop platform technology for any cell type that may have therapeutic potential, and to figure out, how do I scale this up? What are the growth factor requirements? What about media? What about bioreactors? So we're investing millions and millions of dollars in being able to, take this in much the same way I've shown you around immune cells, and then, to use it to treat almost any disease there is. And as I said already, there's massive numbers of clinical trials, and retinitis pigmentosa, macular degeneration, Huntington's, stroke, MS, epidermolysis bullosa, rheumatoid arthritis, autoimmune disorders, et cetera, et cetera. So, we're cell agnostic and we're therapy area agnostic. And again, without dwelling on it too much, you start to leverage the whole enchilada. I mean, I have 2,000 engineers sitting in upstate New York who work on everything we do in General Electric, and they're all hired guns, and it's all kind of like, they don't belong to any of the businesses. So I have guys who, spend 50% of their time working on jet engines who are working on my bioreactors, nano guys and material scientists. I have 800 software people sitting up above San Francisco who just do nothing but internal software development. So you start to pull all of this together, and you can fundamentally change the world of cell therapy really fast, and we have in a big way in the last 5 years. So right now, we're probably a world leader in people using our technology to grow cells. So that's where we're at now. Okay, now it's not going to advance. What's it doing? Whoops. Okay, so the other part of my job is I'm responsible for our kind of 5 to 20 year strategy of what do we do next. As I said at the beginning, somebody 10 years ago thought we should be a cell therapy company, so what do we want to do in 10 or 20 years? So I have a team of about 50 people worldwide who all have day jobs, but who have volunteered to be part of my Blue Skies team. And basically what we do is we just look at next generation technology. And so these are just some of the things we've looked at. They're not in any particular order. I'm going to talk very quickly about 3. I'll talk about 3D printing, I'll talk about in vivo diagnostic imaging, and I'll talk about machine-brain interfaces. Those are all things that are really interesting to me. So I'm sure everybody knows a lot about 3D printing. Already at GE we have about thousands of printers, and we're printing parts for our jet engines, printing parts for some of our oil and gas, because you can print at about a 10 micron resolution, which is much better than you can fabricate. So a lot of the really fine, really crucial components for different technologies, we actually print because the tolerances are so much lower. The state of the art in biology is not particularly good. This is decellularized trachea or trachea. So basically you go to a cadaver, you isolate a trachea, you strip the cells off of it, then you take cells from the patient who needs a new trachea, you put them in with the decellularized one, which maintains the shape and structure of the thing, but doesn't have cells in it. And you put it in a bioreactor and you grow it up and you implant it. This is not scalable because it's so different than organ transplantation. You're never going to get what you need. You can make ears. These are just collagen molds, and you just spray paint cells onto them. There's not even any printing involved here or there. A disc, some facial reconstructive stuff, which is mostly done with ceramics and metals. So we looked at this and said, hey, we can play in this space. We've done all of this stuff. Here's where we're at now. This is just, the next generation. Let's just make hearts and livers and kidneys and other things. So, and the business model for this is really simple. 90% of people die awaiting transplantation. They will never get a donor. And in a more sophisticated analysis, if you look here at the various organs, and you look at the time to implantation, you can see, kidney is probably the one exception where, people can remain on dialysis for extended periods of time, and you can get living donors. Some people will donate a kidney. For these other tissues, the numbers keep going up, and then they fall very dramatically as people die. Okay, 90% of people do not ever get a transplant. And the bottom line is, if you're not transplanted really within the first 6 months, you'll never get transplanted, whatever your disease is. Now, interestingly enough, so I've done a lot of work in the heart. I'm part of the British Consortium on Cell Therapy in the Heart. And if you look at patients in heart failure, they've lost 30 to 60% of their left ventricle. Most of those folks don't need a whole heart transplant. All they need is a piece of left ventricle, right? Because they've got a big scar in their ventricle which prevents them from pumping blood very well. So if I can make a piece of heart about that big and about 3 centimeters thick, and I can mold it into their heart, either sew it in, glue it in, whatever the technology is, I can probably drive most of these folks out of heart failure and restore the heart back to at least part of its normal functioning. So I'm not going to, we spent 6 months mapping this out exhaustively, and this is just, here's some easy stuff. I already showed you the trachea, intravertebral disc, and this guy, again, are just collagen molds. This left ventricle patch is a really important one for us, and it builds on the capacity that we have in Cardiff around heart, because I've got all these guys who've been making heart cells for the last 5 years, so we know everything there is about making this thing. And breast reconstruction, for obvious reasons, following quite radical mastectomy. And then these guys are way off. And then there's a whole workflow here, again, in time, so you're going to have to image, if somebody needs a trachea, you're going to have to image them probably with MR or with CT to size it appropriately. Then you've got to take that into a model that will allow the printer to work. And this in and of itself is really, really difficult. So imagine this is a lymph node, but imagine it's a piece of heart. And again, if I'm going to make a heart construct this big and that thick, I need to know what the real heart looks like. So our plan is to take a real heart, take a big chunk out of a cadaveric heart, and you section it in 5-micron sections, all the way through the 3 centimeters. And then using our multi-omics approach, I will identify the identity of each and every cell in this one section and its position, and then build up a 3-dimensional map of what that piece of heart has to look like, including the ability for it to be vascularized outside the body, such that when we implant it, it's ready to go. So you take that, you build a 3-dimensional, this is a computer-assisted design program, and that allows you to print. Now the problem is, my piece of heart that is going to have about 700 million cells, and I've got to be able to print it in about 2 hours. So if anybody's got any bright ideas about that, I'd be happy to hear them. Okay, so you have your CAD diagram. Don't know what this is. This could be 3D printing, this could be lithography, have no idea what this is. Bioreactor, again, so all of this is really blue skies. We've got, where it says GE, we've got capability technically in terms of this, but nobody's tried to do any of this yet. Okay? So, maybe in a couple of years we'll have intravertebral discs and menisci. Maybe in 5 years we might be able to print something simple like a trachea, and maybe a heart construct. We'll see.
Excuse me,
yeah.
You said 700 million cells, but do you need to print it to that resolution?
Don't know. That's a question we argue about. I've told my guys yes, because I want to push them to do as much as we have to, in case that's what we do have to do. We thought about maybe having predefined clusters, and then maybe you'd only have to print 100 million of those. Just don't know yet. Yeah.
There is current research on that. People are printing cells in cell aggregates.
Organonova?
Not only them, like there is a lot of...
yeah, but they're mostly fibroblasts and even organonovas, liver constructs. They're only 8 layers thick, and they can't get beyond that because they haven't figured out how to vascularize. And they're actually not printing, they're dropping. Sorry. We've done a lot of competitor analysis.
Just to help that, the reason you're replacing these cells is because the previous cells didn't get enough oxygen and then died.
That's one of the limitations, but there is current research on that.
Yeah, we've looked at this pretty exhaustively. We know what everybody's doing, and we're talking to the best people in the world. Because we obviously aren't going to do this on our own. Okay, let me finish because I got 2 more things I want to take you through, and then we can open this up. So, the ability to track cells. Okay, so you have stem cells in your brain that generate new neurons every day. How many people do that? Everybody? Okay. Huh? Yep, down here. Yep. So we got interested. So I came out of Rusty Gage's lab, and he was the guy really who was the pioneer in what's called adult neurogenesis. And almost all the work had been done on rodents because obviously with rodents you can label them and you can kill them at different time points and stuff. There was very little work in humans. So starting in about 2004 in my lab at King's, we began to work on this with human autopsy material. So here's a woman who died about 6 days after having a fairly significant cerebral infarct here. Here's the ventricle down here. When we serially took this to reconstruction, what you see is here's where the cells reside, and they give rise to maybe 10, 50 new neurons a day. Here's our infarct up here. All these brown dots are stem cells, or cells that are in the process of differentiating. And this is in a single slice at a single moment in time in her brain. When we reconstructed the full thing, she's got millions, probably hundreds of millions of cells migrating from this neurogenic niche, as it's referred to, all the way up here. Now in the rat, we know this lasts 2 weeks and most of the cells die, but that's because when you do this kind of infarct in a rat, you destroy about 40% of its hemisphere. And nothing's going to survive there. It's just a big crater. The fate of these cells, we have no idea. We know it goes on for an extended period of time. We've looked at a number of patients like this, and this program is still active months later. And the cells are not migrating over here, they're not migrating down there, they're only going to the region of infarction. But what happens when they get there, we have no idea. Does this mean anything? Nature's pretty parsimonious. Why would this brain be generating hundreds of millions of cells for these cells just to do nothing? And yet we can't follow this at all. We have no imaging capability that allows us to know what's going on in this. So we're working on that as well. This is another one of our Blue Skies project. How can we track these cells using MR or PET or SPECT or CT? And then this is the killer. Hope you guys are ready for this one. Meet Eddie. So this is Eddie Chang. Ever met a neurosurgeon named Eddie? When he called me Dr. Minger, and I said, no, you got to call me Stephen. He said, no, you got to call me Eddie. So Eddie's a maniac, and he's probably one of the smartest guys I know. So Eddie is a neurosurgeon who specializes in epilepsy, and he specializes in epilepsy where patients have seizures in their left temporal lobe, which is where all of our high real estate is, right? Almost all of us in this room, even if you're left-handed, you will be left temporal lobe dominant. And that's where your speech center is, that's where your motor strip is, that's where speech recognition is. All the things that really are cognitively and behaviorally important sit there. And you've got seizures in there as well. So the idea is if you implant a grid of electrodes onto the surface of the brain, can you delineate the seizure area from high real estate areas and then go in and microsurgically resect that? And so this is work that we were doing back in Minnesota in the 80s. The difference was we had about 64 electrodes. Eddie's got 1,000 electrodes in these guys' brains. And he records from them for 10 days to 2 weeks awake, okay? Recording 1,000 channels constantly over that 10-day or 2-week period. Talk about data, okay? What he's managed to do with some of the electrodes which are not near the seizure areas, he's actually been able to map out in the brain function on an electrode by electrode basis. So in a paper these guys have published like 3 papers in Nature and Science in the last year. And what he shows here is there's a set, each one of these columns represents a single electrode. And what he's shown is there's a group of neurons here that respond to really hard consonant sounds like pa, da, ka, ra, but they don't respond to other sounds. Although, some do, but not all. And then there's a group of electrodes over here that respond to more complex sounds like o, ah, e, a, u, and some others that respond here. So he's mapping out speech recognition. Okay? Then the next plan is to not record, but to simulate the same spot, the same electrode. Does the patient now hear da, ka, ra, even though nobody has spoken it? Okay? Then the next thing to do is to then go into the speech production area and do exactly the same thing. This is a little more complicated, but it can be done. And then the idea is so Eddie thinks he understands the neural code behind this. He understands the frequency and the amplitude of when a patient would hear da, ka, ra. So what if you turn it around and say, okay, what's the neural code for when you say da, ka, ra? Okay? And if you can map that out, then in a patient who's had a stroke, over their speech center who's become aphasic, can you now take that and stimulate somewhere else and get the same underlying cognitive behavior? In essence, can you give somebody back a new speech area? Or in somebody who's had a big stroke and they've lost, motor, become hemiplegic, can you now take that part of their motor strip and move it somewhere else? So the whole idea is, can you rehabilitate the brain following spinal cord injury, motor neuron disease, stroke, vascular dementia, et cetera, et cetera. So Obama put up $100 million for this brain initiative, and Eddie's consortium at 3 different universities got 71 million, of which Eddie's individual lab got 26 million. Okay, this guy's he's out there, but he and I share this really common interest in the idea that can you really regenerate parts of the brain that have lost function, either restoring it, more likely not, but moving it somewhere else, and basically retraining the brain. So that's another Blue Skies project we're working really hard on. We haven't quite figured out how we're going to help him yet. He wants 100,000 electrodes next year. Okay? And with that, that's just some mates of mine. John Gurdon, who won the Nobel Prize a couple of years ago for cloning. Martin Evans, who won the Nobel Prize back in, I think, 2007 for human embryonic stem cells. And Steve Dunnett, who was one of the pioneers of using human fetal tissue in Parkinson's disease. And David, I finally have finished. Thank you.
If we want some of these blue skies projects to come more quickly, if we think regenerating broken parts of the brain is good, or if we think it's good to be able to regenerate hearts without having to wait for heart transplants, do we just have to hope that GE is going to bring more engineers, or are there other things in society that might influence the speed at which this happens?
So the one thing is, that I think has made the biggest difference of late is pharma has really taken a big interest in this. Years and years ago, people would say, "Oh, how long is this going to take?" And everybody said, "Well, if there are only academic organizations working on this, where are the big technology companies like GE? Where's pharma?" In the last 5 to 7 years, you see pharma really jump into this in a big way. And almost every major pharma company has some sort of regenerative medicine program. They certainly have targeted immunotherapy programs. And some of them, like J&J and Pfizer, have already been to the clinic. And so I think A, that's a big thing. B, governments, as always, there's never enough research money. You can take things too far because, here in the UK, certainly the Medical Research Council has said if you're not doing translational research now, we're not going to fund you. So, I think that's, going too far the other direction. But, it's always going to be about funding. It's always going to be about, commercial involvement. It's happening very quickly, though. I mean, I've been in this field for roughly 25 years, and I'd say in the last 5 to 7 years, it's just accelerated very, very fast.
Just one more question from me, and then we'll take a few questions from the floor. We won't go on for long because I know people will be getting uncomfortable sitting for 2 hours. You referred briefly to the incidents, the law going through the Parliament this week, I think, about should it be legal to create babies with 3 parents. Is this something that people should be doing to make that change happen more quickly, or do you think it's already, in view of the opposition that's been expressed in the last few days, again by some of the religious cardinals and others?
I mean, the religious opposition's been interesting because the Anglican Church, in terms of animal-human hybrid clone, they didn't have a problem at all. I mean, the
Anglican Church is a broad church.
The former Archbishop did not like it, but we got broad support from the Anglican Church. The Catholics obviously were opposed to anything that has to do with reproduction that is not done naturally, I guess is the word. I've been surprised that the Anglicans have come out against this. I mean, people should. The bill is expected to pass, but I'd encourage people, if they've got very strong feelings about this, you call your MP up or write him a letter or something. That's the only way we got the hybrid embryo bill passed, was that we engaged very heavily with Parliament. And I even had one conservative MP come up to me who said, look, you know, I'm to the right of Margaret Thatcher, I'm anti-gay rights, I'm anti-feminist, I'm anti-abortion, I'm anti-IVF, I'm anti-everything. But you guys have come in and you've actually educated us. And he said, my constituency will think I've gone doolally. I'm going to vote in favor of this. And he said it's only, and the only reason the final bill passed was because a number of conservatives voted in favor where they probably wouldn't have traditionally.
Fantastic.
So public involvement with the government is crucial.
So questions from people who haven't spoken before. One at the back there, yes?
This is more philosophical than technological. I just wondered where you stood on Aubrey de Grey's feelings that we ought to be looking more at preventative rather than reactive medicine.
Oh, that's one of the wiser things that Aubrey says. Aubrey and I are good friends. I agree with you completely. I think prevention, you know, you only have to look at the epidemic of obesity. Probably not, well, here it's bad enough, but you know, in America it's unbelievable. Preventative medicine is crucial, and we don't pay enough attention to it. I thought you were going to ask me about living to be 500.
Yeah. Okay. You are one of the advisors on SENS, is that right? Do you have an advisory role for Aubrey's SENS?
Yeah, in essence.
Right. Roland?
You talked about turning soma cells into stem cells. You talked about turning stem cells into specialized cells. Have there been any attempts to program cells so that they go through a sequence of steps that might possibly solve your cell growth problem?
Yeah, so
for example, you put in a leukocyte, it swims around, it multiplies like mad, and it looks for that scarry heart tissue or the brain. It turns itself into a stem cell. It does what stem cells do best. Okay, that would be a bit of blue sky.
Yeah.
In the direction of.
I don't know of anybody who's done that, but instead of, remember I said you take a skin cell and you turn it into a pluripotent cell and then you figure out how to make it into a neuron. What people are starting to do now is called direct reprogramming. You take a skin cell and you turn it into a neuron without going through the IPS route. And that's been done for 3 or 4 different cell types now, and it appears to work. It's too early to say whether, and you know, that would also, you wouldn't have to bank IPS cells. Then going back to the question over here, you might be able, if somebody, you know, has not a really acute disease, but somebody who, let's say, you know, comes in with a heart attack and they're going to go into heart failure, you basically take a skin cell, turn it into a cardiac cell, and then go in as quickly as you can. So that looks interesting, but how well it'll work across the board, we don't know.
Joe?
I wanted to ask about a very common ailment that a lot of people have, probably people in this room, which is about the disc. You mentioned very quickly, very briefly, you mentioned about the disc. I keep hearing, for loads of years, I've heard that we're only a couple of years away from creating a disc from, say, my own stem cells.
Yep.
Are we there yet?
So one of the, I won't tell you who it is, but one of our collaborators is in large animal models already with IBDs. They're very simple to make. It's a collagen mold, your cells, put in a bioreactor. I'd say we're probably 2 years.
2 years away, right.
Well, that's
But in terms of actually having it done, instead of having a plastic one.
Yeah. I mean, you know, it's going to have to go through the usual phase 1, phase 2, phase 3, and FDA approval and all that. So, you know, you never know how long that's going to take. But right now, I think we're in sheep, and it works.
So I'm curious because you mentioned a lot of research being done out of the US or the UK. From a global perspective, is it US and UK researchers that are going to at the leading edge, or do we have people in other parts of the world?
Yeah. So in Japan, for example, they've already started the first trial of iPS cells in patients with macular degeneration. So that was first in the world. There's a lot of stuff going on. I mean, I spend a lot of time in China, and China is just accelerating rapidly. And, you know, people worry about the ethics of doing stuff in China, but most of my friends in China who are at the leading edge of this, they all trained in the US or Europe for 10, 15, 20 years and then went back for the amount of money that they have for their research there. And the Chinese, particularly in the new regime, they've come down really hard on people doing unimproved therapies. So I'd say it's Europe, Asia, Singapore to some extent, but not as much as you might think. But Europe and North America predominantly.
Question over there with the, yes?
Most of these therapies have been proposed to prevent this, to cure diseases. Is it feasible to try to implant cells and organs in order to increase lifespan in people who are not necessarily diseased?
That's an interesting question. So one response I'd say is I never use the word cure. The only time I would use cure is in those cancer patients who do appear to have been cured. Generally, when you go in with a cell or gene-based therapy in a disease, you don't eradicate the disease. You're improving the disease, but the disease is still there. So it's not right to say cure. And whether or not you would want to, I mean, would you really want to undergo a heart transplant when you're 50 if your heart's still working reasonably well? That's a pretty invasive therapy, I would argue. So I don't know. But enhancement is definitely something that people talk about. You know, if you can make really good muscle cells, for example, and we know that injecting new muscle cells gives you more muscle mass, it's sort of like growth hormone. You know, should you be allowed to do that or not allowed to do that? I think, you know, and we haven't talked about any of this, but availability of these kind of therapies worldwide. You know, my boss used to tell me, you know, don't ever come to me with something that's only going to work in the first world. Anything we want to do has got to, you know, has to work in Botswana and, you know, in Paraguay. So I think availability of these therapies at a cost that people can afford is going to be crucial. They're going to be expensive early on, but hopefully as we scale and technology improves, they get cheaper. But whether or not people should be allowed to have them if they don't need them, I don't know.
The blue jacket? Yes?
I work in clinical trials with oncology, so I was very interested in the cellular screening that you presented. I just wonder, because the whole body mechanisms are obviously very complex, you know, with current pharmacodynamics and pharmacokinetics profiling, do you believe that in the future we'll be able to do a whole screening on a cellular level without clinical trials?
Doubtful, I think, at least in the near term. The most radical thing I'd ever heard was we were on a call with the FDA and they were looking at the second round of data that I showed, the really big data set around screening for structural cardiotoxicity. And we were looking at the whole 150 compound screen and all the other assays. And somebody at the FDA, a very senior guy at the FDA, said, you know, looking at this data, it makes me wonder if we really need to do in vivo toxicology anymore on animals. And it was like you threw a bomb into the room. You know? We all started yelling, what are you talking about? And I thought that was one of the most radical things I'd ever heard. So the idea that you might, I mean, you know, it's all about proof, right? Risk-benefit ratio. If you could convince the FDA that my body in a chip is equivalent to a body, and you know, and if you, I mean, it's the thing we had to prove to them. You know, they're like, well, how do we know that we can trust this? Validate this for us. And then you just have to take them to a point where they go, okay, now I believe it. So body in a chip may do that. I don't know. You might need 50 or 500 bodies. I don't know, or cells from different people, which, you know, IPS could give you that quite easily. But whether or not you'd ever not need clinical trials, that's a really interesting question. I don't know.
Katarina?
Yes, when you talk about making organs in the long term, like we spoke about liver, heart and so on, what do you mean by long term? I mean, you know, you said the short term would be like 2 years, medium term like 5, or is that a philosophical question?
It's kind of philosophical at the moment because, you know, we you know, as I showed you in the map, we know what we think we know what the bits are, but you know, like the fabrication step, I don't know what that is. And if you look at what people are doing currently, it's really rudimentary. It's not fast. It's you know, it's not defined. The CAD programs aren't very good yet. The printers aren't made for this. I mean, the printers are made for metals and plastics. You know, and we talked to all the major printing companies, and none of them have anything that's even close to being ready for biological applications. I don't know. You know, 5 to 20 years, which is blue skies.
But I mean, long term would be something around 10 to 20 years, not something like 50 or 100 years.
I don't think so. I mean, my ultimate aim is, you've ever seen Fifth Element? So I want to make Leilu. Right? Just, you know, stitch somebody, you know. And you know, down the road, I think, you know, for some applications, we'll actually be doing printing on people themselves, rather than, you know, making a construct, bioreactor and growing it up. You just do it in vivo. So I think that's another application down the road where, you know, you do a surgical procedure and you do the printing in situ.
Yates?
You know, I was wondering if you could comment on, like, to what extent you see the impact of these sort of alleged exponential changes in technology on your sector. I always thought maybe when it comes down to knowledge on the field, there's a slow, a slight reduction. You can't quite keep it exponential because you have to test it on. There's certain things that would take time. So do you see it accelerating? Do you see the acceleration? Do you see evidence of acceleration as much as we would say in other fields of technology, or maybe a little bit slower, or what kind of? What's your gut on that kind of feeling? The exponential idea is that at some point we have no idea what's going to happen next year because we won't even know. It'll be like,
You ever seen Peter Diamandis talk?
Of course.
I mean, he just,
Yeah, of course. But does it translate to medicine?
I think so. Can I show one more video? I don't know how many of you have heard of HoloLens?
Yeah.
Yes.
Have you seen what it does?
Yeah.
I think it's worth showing it. Yeah?
Okay.
So this came out just a few days ago.
So I was in Seattle about. Come on, go back.
So you're offline perhaps?
No, I should. Yeah, but I should be able. See, it's playing. Okay. Maybe I lost it.
So people should look at Microsoft HoloLens and the points you would emphasize from the video.
So I was in Seattle 10 days ago, 2 weeks ago, and I tried it on, and it is absolutely mind-blowing. So there's a pair of goggles you put on, it's a pair of glasses basically you put on, and the real world is there. It's not altered reality in any way. It's real world, but it's augmented reality because basically you have a keyboard up here, and you just walk around and you just finger tap. So it follows your eye gazes. And so like how when you single click, it lights a icon up, but when you double click, it opens. So with your eye, it single clicks, and then you just go like that, and it opens it up. And you can put the keyboard in, you can take things and put them on the wall, you can redecorate your living room.
And is this just Microsoft hype, or did you actually experience that?
I tried, so the thing I did, which was really cool, and it shows in the video, is the motorcycle thing. So you've got the device on, you've got a computer screen in front of you, and you've got a CAD diagram of a motorcycle. But you can't do anything with it. So you take it out and you put it on a tabletop. And now I can spin it around, I can expand it, I can shrink it down, I can do anything I want with it. Then I can start to make all sorts of alterations. I don't like the handlebars, I don't like the mirrors, I want a bigger gas tank. And you do that all on the virtual model, and then you save, and then you go apply, and you walk over to the real motorcycle, and all of the virtual stuff's been put on top of it. And it's real. I mean, you look at it, and you can't tell the difference between the real motorcycle and the bits that have been virtualized. And somebody else can be looking at exactly the same thing 10,000 miles away with their goggles on. And it's just mind-blowing. And you're no more keyboards, no more being tied to a computer, no more having to sit at a desk. You just walk around.
No more risk of a heart attack while sitting on the desk.
Exactly. I mean, it's really incredible. The applications, and particularly in medicine, I think are going to be phenomenal.
And crossover with the work that you're doing?
A huge amount. Huge amount.
So we could talk a lot, we could keep going a long time. I think we should draw it to a halt. I'll come back to Stephen and Dr. Minger in a moment. Just very quickly, a couple of announcements. Some of the stuff we discuss here is also the social implications of some of the technology, and the technology is fascinating. There are social implications. After all, you had robots who were kicking all the humans out of the labs. This is happening all over the world. What are the humans going to be doing if the robots are doing all our work? We are discussing that in 2 weeks' time in Birkbeck, and we're going to be discussing the possibility that we need to make, just as we're restructuring technology, we need to restructure some aspects of how the welfare system works, and we're looking at the case for so-called basic income, which is a radical and controversial idea, but it has support from people right across the political spectrum. So we'll have two speakers from the basic income campaign group who have been answering these issues in their own research for a while. So that's happening in 2 weeks' time. 3 weeks after that, we're looking at another aspect of the future, which is not kind of on the individual level, it's on the whole global level. And it's looking at where are we on coping with the environmental issues of potential climate change and runaway climate change. And we have a speaker coming back who has spoken to London Futurists before. His name is Jeremy Leggett. He has a long history of working inside the oil industry, and then as a green campaigner, and more recently as a solar entrepreneur. He is a very interesting writer. He writes about his experiences in very interesting books. books, and he's producing a new book shortly, and he's going to be giving a sneak preview of that book. It's called Winning the Carbon War, so it's an optimistic vision as to how things might be changing around after lots of doom and gloom on that front. So that's happening 5 weeks' time in this building. We also, some of us look at some other political issues. Some of these are covered in Hangouts. There's a Hangout happening tomorrow night. Some of you may want to be interested in. It's you can find it online. It's on the case for. We've got some people coming on to talk about something called anarchist transhumanism, which is two words that don't very often go together. But is this the case for taking advantage of technology to restructure society so there isn't a centralised state anymore, but there's much more kind of a cooperative interaction? So that's one thing that's happening. And the other thing that's happening in the future is in about 15 minutes' time, some of us will be in the Marlborough Arms pub discussing this topic and several other topics. And you're welcome to join. It's just a 10 minutes walk away. There's maps outside how to get there, or you can follow along with some of us. And Stephen told me at the beginning he thought he'd been needing to stop and pause because he's been a bit under the weather, but somehow the enthusiasm kept you going, and the good material kept you going, and the audience kept you going. So let's give a special round of applause.
Thank you very much.